We are continuing this module 5, Behavior and Design under Flexure. In particular, we are focusing on how to use the IS code provisions for calculating the amount of steel for different scenarios. So, in this part of the video, we're going to talk about how to design the doubly reinforced sections using IS code provisions. Okay, we'll also compare some of the analysis that we have done previously using the moment curvature analysis and see how the IS code calculations are comparing with the IS code moment curvature analysis that we done in the previous part. Right. So we have seen the previous cases, right? For a particular sectional dimensions, once grade of concrete and grade of steel is fixed, it has a limiting moment of resistance. How does this limiting moment of resistance comes? To make sure that the steel is going to yield, reach its yielding strain. What is the yielding strain as per the IS code? It is 0.002 plus 0.87 Fy by elastic modulus, which is ES, right? So that amount of strain has to be reached by the steel when the concrete is reaching 0.0035. So the force distribution and the moment resistance that is corresponding to that strain condition is what we call it as a limiting moment of resistance. At that time, your nodal axis depth is also going to be higher. Now, there may be situations your moment demand from your analysis may be higher than what you can have for a singly reinforced section, that is your MU limit. So, in this case, MU is going to be greater than MU limit for your singly reinforced case. Okay, so the capacity is going to be less for singly reinforced section, and reinforcement is provided only on the one side. Okay, in that case, then I cannot put more steel than your AST limit or PT limit that what we have discussed in the previous case. But then your steel will not reach its minimum required yield strength. Then in that situation, the only way we can achieve capacity is to go for doubly reinforced section. That means I need to put some steel on the compression side, and then I can go and put more steel on the tension side that will give me more moment resistance. Sometimes when we do the analysis, we need to reduce the stress in the concrete and transfer the load to compression steel. This is particularly very effective whenever your members are undergoing creep. Putting compression steel will actually help in reducing the creep of concrete, and it is going to help in reducing the stress levels in the concrete under service stress condition. If you want to limit your stress in the concrete due to some design requirement, then providing compression steel will help in reducing the stress levels in the concrete for a particular service moment, right? So again, we have seen it in the previous parts of the module. Providing compression steel will help in reducing the sustained load deflection, because for short-term deflections, when the load increases, deflection increases. But when the load is remaining constant, the deflection will not remain constant. The deflection will keep on increasing. That's what we call that as long-term deflection. That happens under sustained load of dead load and some fraction of your live load. So in that case, if you want to reduce your sustained load or long-term deflections, then we can go ahead and use compression steel that will help in uh, uh, reducing your long-term deflection. And sometimes you put this also some minimum hanger bars at the top in creating the reinforcing case. These are the scenarios in which we go for doubly reinforced section. Some of the advantages of going for doubly reinforced section. Now let's see from internal force point of view, when do we go? So we have taken this section, a simple section with reinforcement on the tension side and on the compression side. Now the compression steel is put at a distance of effective cover of D prime. Okay. Now when you do this compression steel, what happens is for us, you end up with less neutral axis depth to achieve the force equilibrium. Then when you have less neutral axis depth, because if you go back, curvature is nothing but epsilon cu by xu. That's what we have done. If your neutral axis is less, depth is less, then you end up with more curvature at failure. Okay. So in this way, by adding compression steel, With less neutral axis, you can achieve the force equilibrium. Then with less neutral axis depth, then you can end up with more curvature, right? And also it helps in changing the failure mode from compression to tension. Okay, so if or in other words, it allows me to go for more, putting more steel in tension side and still retain my under reinforced failure mode, provided I also put a lot of steel on the compression side. So by going for doubly reinforced section, we can convert a singly reinforced section that is going to fail in over reinforced or compression mode into tension mode. Okay, right. Now let's look at it from IS code provisions. Again, we are looking at design stress strain curves that are specified by IS 456 for concrete in compression and for steel in tension. So now let's look at the ultimate condition. I've taken a simple doubly reinforced section like this. Okay, so this is your failure condition. Epsilon Cu is 0.003635, and then we are calculating what are the strains in the different steel. Now you see, now that I have put some steel on the compression side at this condition, depending upon the neutral axis depth, I can calculate what is epsilon Cs. Now what is epsilon Cs? You can look at it. We can, from your neutral axis depth, Xc max by 0.0035 from similar triangle should be equal to, what is this distance of the compression steel? It is going to be Xu max minus d prime by epsilon c. So from here, I can calculate what the strain in the compression steel. Okay, it's just from your similar triangle. Okay, nothing fancy here. Right. So again, so when do we go for going for a doubly reinforced section? When your moment demand is greater than mu limit, compression steel is provided to ensure that under reinforced failure mode is preserved. Okay. So from the strain distribution, now we can calculate your epsilon SC. Okay, that's what we did. So from a similar triangle, you can calculate your epsilon SC because this is your strain. From a similar triangle, we can do that. Now for a particular section, so I am doing the calculation at XU max, okay, so that we can see what is that additional moment resistance that I need. For that, how much is the compression steel that is required, okay. So this is the difference. Mu limit is given to you to preserve this failure condition, right? So if your demand is mu, the difference mu minus mu limit should be provided by this compression steel, right? So that still, so we will look at now how do we get this, okay? So, but for this to calculate what is the force that is required from a compression steel, I need to know what are the stresses. Now, how do we calculate the stresses? Stresses, I have to calculate it from your epsilon SC that we have calculated from your similar triangle. Okay, so once it is known, then we can calculate it. Then what we this additional steel that what I am providing, so that is basically, let's say that which is nothing but your AC multiplied by FSC, which is the compression force that we are getting, which is your CS. This should be equal to the additional steel that should I provide on the tension. Now that I have kept this Xe max, that means here in the steel is going to reach yielding strength. So that should be equal to my AST1 times point. Basically, we call this as, let's say, AST multiplied by 0.87 F5. Okay. So, or in other words, what would be your additional tension steel? AST limit. Okay, the total steel. Now this is your additional steel. That what I'm going to put. So if you substitute that, so what would be that? So this will be your force contribution, right? So from here we can get the additional steel that I need to put it on the tension side. Okay, so now let's see how to do this analysis. So that will have two components. One is the AST limit that is coming from a singly reinforced section, plus what is the total additional steel that I need to get. Okay, so this would be your force. Okay, Now let's run one example problem, then it will become very clear. Let's say I take the same section with 400 mm by 600 mm depth, and I'm taking characteristic strength of 40 megapascal and grade of steel is 500 megapascal, and my moment demand is now 1500 kilonewton meter. Okay, again exposure condition is same, moderate, and we have seen that in the previous case when we did the calculation, mu limit came out to be about 646 kilonewton meter. So clearly the moment demand is higher than mu limit for a singly reinforced section for this dimensions. Okay. Now let us see how do we do that. I'm just running through the numbers again. For the given exposure condition, we are taking nominal cover of 30 millimeter. So the effective cover will become clear cover plus the stirrup diameter. So this is your stirrup. Okay. And this is half of longitudinal bar. Okay. So I'm assuming that I'm going to use 20 mm bars. Sometimes we may have to revise this also. It may not be adequate. The number of bars for 20 mm may not be adequate. So you may have to put 28 mm or 30, 32 mm, depending upon your requirement. Here I am taking the 20 mm angle. So the effective cover works out to be 50 mm for both top and bottom. So in fact, I'm going to use both top and bottom same diameter of steel, which is 20 mm longitudinal bar. So the effective depth for tension is basically 550 millimeter. Now we have derived this limiting moment resistance. Okay, it is purely function of your XU max by D, and then for a particular grade of concrete, we can calculate your MU limit, right? So this is just the moment resistance that we are taking in terms of your compression force, right? So if you this is directly given in your IS 456, this also we derived it in the previous part of the module, right? So you go back and let's plug in these values and see what is your MU limit. Okay, so for FE 500 we have calculated, we have already derived based on the strain condition what is XU max by D, which is your 0.456, right? So you plug into this equation, then you get Xc max of 250.8. Then you put it in this MU limit equation. Xc max by D is 0.456. This is 0.456. Then FCK is 40 and effective depth is 550 and width is 400. So you plug in these numbers and you get a value of 646 kilonewton meter. So this is the maximum amount of moment resistance this particular beam of 400 mm by 600 mm can give when I design it as a singly reinforced section, making sure that the steel is just going to yield. Okay, it's a balanced capacity, right? So now I need 1500 kilonewton meter, which is not adequate. So it is clear that we cannot design this section as a singly reinforced section. So I have to put some additional steel on the compression side. In addition to that, I also put some additional steel on the tension side so that both of them will give the additional moment resistance that is required for the demand, which is 1500. Now let us see how to do this process. Okay, as we have explained. So the first thing is we see what is the expression. This additional moment resistance has to be given by this force multiplied by this overall lever arm. Okay, so when I take moment about this distance is basically this is your d prime. This is going to be from here to here, it is going to be d minus d prime. So when I take moment of this force about this tension side, it is going to be cs multiplied by d minus d prime. Now what is cs? So this is the moment resistance that is coming from your compression steel. Okay, okay, so what is CS? CS is going to be, I don't know what is the force, FSC, we call it, and AAC, the amount of steel, multiplied by D minus D prime. So I am calculating AAC. So if I substitute that, so now that for this given problem, from this again, we know what is the strain in the steel, compression steel, right, from your similar triangle. Now that I have fixed this point 0035, so I can calculate what is the strain here at this location. Okay, from similar triangle. So that we have done. So because the compression steel is at a distance of d prime from the top. Okay, so for XU max distance it's 0.0035. For XU max minus d prime distance, it is going to be using similar triangle, we can calculate that. So it works out to be 0.0028. Okay, now we have to use the design stress strain curves which are specified by your code. Okay, so now let's look at how that curve, because I need to calculate the stress in the compression steel to calculate this, right? So if you look at your stress strain curve for compression steel for Fe 500, so this is how it is. We have discussed this previously. Now for a strain of 0.0028, you see here. So we have seen this when it is less than this value, you can directly multiply. So from this region to this region somewhere, okay. So we have to use this table, okay, which is there here. So for example here 0.0028 is what we are looking at. So we are looking at this point 0.0028. Okay. So for this it works out to be stress of somewhere here in between. Okay. So it is very close to this point because it's 0.00277 is 430. For 0.0028, which is slightly higher than that, it will be 413.9. Now I got the stress, so I can calculate the uh, what is the area of steel for when this compression steel is at this stress. So that works out to be okay. So this is the additional moment resistance that I need to get. Okay. So this is your MU limit. This is your demand. The difference has to come from this compression steel lever. That has to be again equated by the tension contribution by from the additional steel that we are going to provide, that we will see. So from this we can calculate your area of compression steel as 4127 mm square. Now this is your AST. One is your AST limit that we have already done for a singly reinforced section. Again, we have derived this, right? So for AFE 500, it is 0.189. So from this, what is PT limit? It is going to be 0.189 multiplied by FCK divided by Fy. So 0.189 FCK by Fy, it gives me 0.0159. Okay, so because FCK is 40, Fy is 500. So when I divide and multiply it by 0.189, so you end up with this value, which is 0.0151. Okay, so again you plug back. So what is PT limit? Again we go back. What is PT limit, or what is definition of PT? It is nothing but your AS divided by B times T. Okay, in fact it is 100. Always it is expressed in terms of percentage. So that is why this 0.189 this is given here. So if you substitute that 0.0159 multiplied by 400 times your effective depth of 550, you get the 3322 mm square is your limiting reinforcement. That is the maximum steel that you can put to preserve that steel yielding, uh, and that is a maximum steel. But that is also going to give me only a limited moment resistance. That is MU limit is 646. Now my demand is 1500, so that additional thing I have to see. So now you see, if is this system, is it in horizontal force equilibrium, is it satisfied? Now we have done C previously CC was equal to TS. Now what I have done, in addition to that, I have also put CS, compression steel. Now TS remains the same. So if I put AST of only 3320, so I need to put some additional force from tension. So that additional force that is coming from this equation, this contribution, which is you should basically, whatever that additional thing that you are putting. Okay, previously this was good. This should be equal to this. That's what we are doing is AST multiplied by 0.87 Fy should be equal to CS, where CS is ASC multiplied by FSC, which when I divide by 0.87 Fy, this is the amount of additional steel that is required to satisfy the force equilibrium of compression force coming from your compression steel, right? So then when you do that, you get your 3929 millimeter square. So when you add them up, so this is your uh, okay. Actually, so this should be Uh, so this should be, I'm sorry, this should be AST limit, which is, this should be 3,322 plus 3,929. So that works out to be your this value should be 332 plus 3,929, which works 7,000. This is not correct. This will be 7 is not correct. 7,251 mm square. So that is the total amount of steel that we need for achieving the moment demand of 1,500 kilonewton meter. Okay, so this is the total demand. Now, what is the compression steel that we have kept is 4127. So that is directly coming from here. So this beam is having compression steel of 4,127 mm square and total tension steel of 7,251 mm square to satisfy the moment demand of 1,500 kilonewton meter. Okay. Now we are taking one more example. So this is example number two. Okay, example number two. And here also we are doing analysis. Now in this case, what I am doing is this is the same cross section that we use for our moment curvature analysis. So now what is that I have? On the tension side, I have a total reinforcement of 9,600 mm square. And on the compression side, I am having a reinforcement of 4,800 mm square. Okay. So this is the section. Now we are going to do the analysis, not through our moment curvature with parabolic model and elastic perfective plastic. Now we are doing the analysis using the design stress strain curves that are specified by your IS 456. Okay. So now let's look at it. Uh, in this case, I'm doing the analysis for a particular amount of reinforcement. I'm not doing design. So we have to do it in an iterative. We have to assume different values of neutral axis depth, and we have to calculate the strain distribution. Then using the stress strain curves, we have to calculate the stresses. Then we have to check the equilibrium, and then when equilibrium is satisfied, then you calculate your moment resistance. Okay, this is a strain compatibility approach. See, the previous case, we were quickly designing a doubly reinforced section for given demand. Here, the sectional dimensions and reinforcement is given. We are doing analysis. Okay, so here you have to assume your neutral axis depth. Okay, so and I'm assuming doing analysis for ultimate condition for a strain of 0.0035. So 320 is a neutral axis depth that I'm assuming. So I can calculate my tensile strain and compressive strain from your similar triangle. Tensile strain works out to be 0.00251. Okay, for 0.00251, you see here, this is somewhere in between 391 to 430. So when you do interpolation, the stress curve, it works out to be 402.6 megapascal for stress. And then stress, this is not, in elastic perfectly plastic, it is very easy. But here I have to follow the design stress strain curve specified by the IS456 and which has different ranges that I need to follow. When it is less than zero point 0.8 FYD, then you can directly multiply by elastic modulus to get where the strain is less than this 0.00174. But here I am in the in-between range where the stress strain curve is non-linear. So we have to interpolate based on the values that are given here. So when you substitute, then you get a tension force of 3,865 kilonewton. Then what we do? Now we are looking at what is the compression steel. Okay, compression steel also from your similar triangle. For 320 mm of XU, strain is 0.0035. 320 minus 50 mm of depth, what would be your epsilon CS? So from similar triangle, I can get, which works out to be 0.00295. Again, design stress strain curve is same for compression and tension for steel. So for 0.00295, it works out to be somewhere here. Okay, so for this, the stress is 417.7. Then the area of compression steel is 4,800 that we kept. The compression force works out to be 2005 kilonewton. Now you see, we have calculated this, we have calculated this. Now what is CC? CC is from your IS code. So what is CC? CC is now 0.36 FCK B times XU. So XU I have assumed, right? Now how do you satisfy the equilibrium condition? CC plus CS should be equal to your TS. But finally, we have to satisfy. Then only your assumed neutral axis depth is correct. So let's see. So this is CS we have got, and TS we have previously calculated, and CC when you put it, it works out to be 1843 kilonewton. So when you add them up, compression contribution of concrete plus compression steel contribution is nearly equal to TS. So the assumed value of 320 is satisfying the equilibrium condition. Now you can ask me, how did I come to 320 directly? We have done that iteration and then we have calculated. So in fact, this should be 320. So 320. So in fact, you can see previously I started with 288, it is not satisfying. And then we, for a 320, nearly it is satisfying equilibrium condition. Then the moment resistance I can take. I can take moment resistance about this point. Now you will have two things, okay? So, right, so basically concrete force is going to create a lever arm like this, and then tension force is going to create a moment resistance with this lever arm. Okay. Now this is, let's see, Z1 and Z2. What is Z1 for concrete contribution force? It is going to be D minus 0.42 XC. Okay. So this distance is your 0.42 XC. Okay. So this is your 0.42 XC. This we have seen. Okay, that's as per your IS code. That is your CC. It is locating at a distance of 0.42 XC from your top fiber. So the distance is going to be lever arm is this. What is Z2? Z2 is nothing but D minus D prime. So this is D minus 0.42 XC. So this both, because I'm taking moment about the tension steel, the tension force will not come into the moment equation. So you get a moment resistance of 1768 kilonewton. Now we know the curvature is 0.0035 by XU, which is 10.9 into 10 to the power of minus 6. Okay, this is the capacity that we can calculate from your IS code design stress strain curves. Okay, in moment curvature we did for the entire range, right? Now we have done for only ultimate condition. Now in this ultimate condition, for example, as the steel epsilon TS has actually not reached the yielding. Okay, so this section doesn't really conform to the IS code because epsilon TS, let me go back and see what is the value that we're getting. So it is only 400. So the strain is 0.00251. Now for IS code, what should be the minimum epsilon tension steel it should have? 0.002 plus 0.87 Fy by Es. That works out to be 0.00407. So this value is less than your yield specified by IS code. So this section actually is not conforming to IS 456. We have just taken this example and it is not meeting the minimum requirement of yield strength. Okay, so it's not actually, though you have steel both top and bottom, it is actually not an under reinforced failure mode as per the IS code. Okay, right. So we got this value. So now I'm just reiterating. This is based on your these calculations are based on your parabolic curve for concrete. If you remember, this is F prime C. Then for steel, we have taken Fs epsilon s. We took this. Okay. When I use this material properties, now what is the resistance that we are getting for your sectional dimension that is given here, right? So if you do this again, you can go back and check your, this is your example 5.7 of your module 5. So you get force of this, and then you get a moment resistance about 2298 and curvature of about 17 into 10 to the power of minus 6. Again, these are all the values that we already did. So you can go back to the previous parts of the module and see how this analysis was done for, we did moment curvature analysis for different strains. Here we are showing calculation only for point, not the ultimate condition. Okay, so you can see that we got this values. Now if we compare this, okay, same sections. One I did using parabolic sustained curve, elastic perfectly plastic curve for steel. Another one is using IS code. So you can see that with actual material property, I get a moment resistance of 2298 kilonewton meter and curvature at failure of about 70. Same thing if I use IS code method, I am getting a conservative estimation of 1768 kilometer meter and a curvature estimation of 10.9 10.9 into 10 to the power of minus 6 per radians per millimeter. So the unit of curvature is 1 by millimeter, right? Or in other words, radians per millimeter. So you can see that for both singly reinforced section as well as for the example that what we have taken doubly reinforced section, the IS code method of calculation is quite conservative. So in this case, if you look at it, it is basically 1768 divided by 2297. If I take, it works out to be about 77%. So the estimation of capacities from a design code should always be conservative than what you are calculating is your actual material properties, right? So in this way, we can say that the IS code method is calculations are quite conservative and quite safe in terms of design capacities, right?